Sometimes it's a good idea to look back on, say, circuits that you have published on YouTube. And I want to look back in this case to a capacitor tester that I have published, say, quite a few time ago on YouTube. The principle is very simple. It's an oscillator, and say the frequency dependent capacitor is connected here to these two electrodes protruding out of the box, and here is the oscillator, and it is very simple. Of course, you can buy on the World Wide Web many more or less intelligent, or not intelligent of course, component testers. They can test capacitors, transistors, be it NPN or PNP or whatever. Anyway, this is only, say, a capacitor tester that in my opinion works very nice. The whole idea is that there is a relation between the oscillation frequency and the capacitor that sets the oscillation frequency. And there is a video on my YouTube channel, and I will give the link. So, and I have already showed this earlier. Here are, say, the different frequencies that the oscillator gives out when a capacitor of a certain value is connected to the oscillator. So, for instance here, a capacitor of 3.3 picofarad gives out a frequency of 1.56 kilocycles, and you can test that with your counter and with your oscilloscope. And that's in a certain way important because this circuit can also measure capacitances of say tiny values in the order of 3 picofarad up to, say, here 150 picofarad and 220 picofarad, and I'm more or less sure that say all these elaborated AI units cannot give that specific value of the capacitor. Anyway, could be that it works also with a more sophisticated AI, kind of AI capacitor tester. But anyway, let's look inside my circuit that I published quite a long time ago. But anyway, I will give the link and the schematic in the description of this video. So, this is the aim of the video, a capacitor test also for small values. Anyway, so here we have the situation. We read now 617 Hertz. We see now on the oscilloscope this waveform. By the way, this waveform is only, say, a kind of indication to, say, the wave that is sent into the circuit to test the capacitor. So, and why do we see that frequency here, and especially the frequency, that's where it's all about. We have here a 4.7 nanofarad capacitor that is 4700 hertz, sorry, 4000, and 700 picofarad, and that relates, when we look at the table here, to 578 Hertz. And let's see what it can bring. We see this on the scope, and we see here 618 Hertz, but of course that has everything to do with, say, the circuit itself, the temperature, etc., etc. So we are more or less sure, or say completely sure, that this capacitor here that we are testing now is 4700 picofarad. Kind of baby. Anyway, let's go, and that's more, perhaps more important to tell. Let's go to the tiny value capacitors, and I have used in this demo by purpose a very small capacitor that was often used in radio circuits of the 1950s, 1960s, etc. Two aluminum plates in a certain way that give out a certain capacitance. I don't want to elaborate on the typical properties of this capacitor, but anyway, let's say it is here approximately 8 picofarad or so, and let's look at the oscilloscope and let's look at the frequency. It's 1.6 kilohertz, and we see here needle pulses. Anyway, so needle pulses 1.6 kilohertz. Let's look at the table. Where is 1.6 kilohertz? Well, it's in the order here of 8.2 picofarad here, or 3.3 picofarad. So that gives you a very reliable indication about the capacitance of this in fact tuning capacitor, because we can tune, we can move the hood here to the lower side, etc., etc. Let me do that, and of course in that case we have a higher capacitance. So I'm tuning now here that hood, put it somewhat down, and we are now say that's the normal ID, in the order of 10 picofarad, 20 picofarad, and these, say, typical capacitors were often used for tuning radio circuits. That is of course logical in a certain way when you know something about the radio. So now it is turned completely in, and what do we read? We read 1.13 kilohertz. This is the waveform, and let's look here in the table. 1.13. It must be here in the order of 27 picofarad, and I think that is okay. And when I look back at this table anyway, 1.18, of course, 1.13, anyway. So we are in this order, 20 2 picofarad up to 27 picofarad. So anyway, I can only advise, do your own experiments. Say, this is a very, very useful circuit to test and try all kinds of capacitors, and when I have time I will now connect a 22 nanofarad cap. Here 22 nanofarad. Let's see what this can bring and whether my circuit that I developed is reliable for, say, useful for everyone. So here is that cap. Now in the of course here 22 nanofarad, and let's see, we have this waveform and we have 301 Hertz. Well, that's such a difference, but anyway, let's look. 22 nanofarad. What must it be? What must it be here? 22 nanofarad is 278 Hertz. Say 300 Hertz. Does that matches that with what we see on the counter and the oscilloscope? Yes, it surely matches. Here we have the waveform and here we have the frequency. So that surely works. This circuit surely works. Anyway, thanks for watching. Of course, you can also buy, say, a capacitor tester, a components tester via Ali, etc., etc. But I think my idea regarding the testing of capacitors could also be electrolytics, though that's in a certain way a different story, but I've tested them and here you see the effects of the electrolytics. Say 33 microfarad, it means 6 Hertz, etc., etc. Anyway, the whole idea is, say, to get a good idea about the properties and the capacitance of a capacitor. Could it be a ceramic type or a polyester type or whatever? Anyway, thanks for watching, and let's look finally on the workbench and where this test was done. The waveform here, of course, and the frequency that every capacitor gives out in this test circuit. Thanks for watching.